Okay. Good morning, guys. I thought that you can see very well. So questions, do you have any questions? You can either speak out or you can put them for me in the chat. Go ahead. Any questions from the homework? You want to take a pop quiz then? Then, okay. Everything you guys, you can write them on chat if you want. So, and I will pick them up. Okay. Any other question beside the one in the chat? Mark? Okay. Right. I think we can start. Okay, so I'm going to pick up 11.3 number 20, no, 11.2 number 35 first, and then 11.3. So let's do that. Okay, so 11.2 number 35. Okay, here we are. And the question is, determine whether the series is convergent or divergent. And if it is convergent, find its sum. So number 35, we have the following series. Sigma k equal 1 to infinity of sine of 100 to the power k. All right. Any ideas? Any ideas? How can I do these problems? Whoever have an idea, in mute and share it.
It's geometric.
It's geometric. Is she correct? Let's write up few terms. Don't let the sine 100 get in the way. So this is the sine of 100 plus, okay, sorry, I'll write bigger. Sine of 100 squared plus the sine of 100 to the power 3 plus, etc., etc., etc. So this is definitely a geometric series. So Laura is absolutely correct. That's geometric. And the common ratio here is the sine of 100. Now, is the common ratio less than 1? Yes or no? You guys know? Yes, because the sine always oscillate between -1 and 1. And so sine 100 is strictly less than 1. You can even evaluate it. It means that the series converges, because that's a geometric series where the ratio is less than 1. And now we need to find the sum. So let us remember the rule for the sum. What is the sum? The sum is the first term, whatever my first term is, times 1 over 1 minus my ratio. And this is equal to what? What is my first term? The first term is what happened at k equal to 1. So at k equal to 1, it's sine 100. So my first term here is the sine of 100 times 1 over 1 minus the sine of 100. Now to find the value, you just have to go pick it up from your calculator and proceed and find it. All right? Is this problem clear? Okay. Let us pick up, go over number 33 in 11.2. I will do that, and then I'll pick up the other one. So let us look at number 33. Here we are. And the question is, let's look at it. We have the following series. Sigma n equal 1 to infinity, 1 over 4 plus e to the minus n. And the question is, does the series converge or diverge? I mean, so far we don't know a lot. But the only thing we know, that's not geometric. So this being ruled out. When it's not geometric, I'm going to start looking at the terms. So what's the form of the term? An here is 1 plus 4 plus e to the minus n. That's how the general terms are. So what I'm going to start looking at, okay, we don't know a lot so far. We know geometric and we know the divergence test. So I'm going to look at what happened to the term when n goes to infinity. So the limit as n goes to infinity is the limit as n goes to infinity of 1 over 4 plus e to the minus n. And now let's ask ourselves, when n goes to infinity, what is the limit? Okay, let's analyze it. 1, 4 plus, it's this term. What happened to e to the minus n when n goes to infinity? It goes to where? Ideas? 0. I'm getting a lot of zeros. Zeros is absolutely correct because, as I said several times, e minus n, one way you see it, is 1 over e to the n. So when n goes to infinity, e to the n goes to infinity, 1 over something very large is very small. So this one is going to go to 0. So this is going to give me 1 over 4. 1 over 4 is absolutely different from 0. So the general term is getting close to 1 over 4. It means intuitively you're starting to add 1 over 4 plus 1 over 4 plus 1 over 4. So the series will, it diverges. Or we can state by the divergence test, by the divergence test, the series will diverge. Okay? Questions about this problem? Great. So now we're going to move to 11.3, number 23. So 11.3, number 23. All right, so let's pick it up. 23. All right, so here we have the following series, sigma k equal 1 to infinity of k times e to the minus k. And the question is, does the series converge or diverge? Now, we rule out geometric. This is not geometric. And the general term here, so they use k, so I'll write k is k times e to the minus k. Okay? And when k goes to infinity, just intuitively, what happened to ak? So just on the side, just for check. So I usually, whenever I see a k, I just glance at it and ask myself, what happened when k goes to infinity? So what happened to a k when k goes to infinity? Anybody? K times e to the minus k. All right, this is equal to what? When k goes to infinity, this one becomes very large, and e minus k goes to 0. Now 0 times infinity is indeterminate. So to find the limit, we're gonna rewrite it k over e to the k. And now we can use, if you want, when k goes to infinity, the numerator goes to infinity, the denominator goes to infinity. Infinity over infinity is really, really very large. So I'm gonna get the limit, we're gonna use L'Hopital's rule, 1 over e to the k. K goes to infinity. And this is gonna give me a 0. Okay, now remember, infinity times 0 is indeterminate. It could be large, it could be small. So we have to manipulate to get the limit. So if the limit is equal to 0, can we say anything about the series? Does it mean it converges? No, absolutely not. It may converge or may diverge. We need another way to figure it out. And this problem, we're gonna use the integral test to figure out whether it converges or diverges, because there is nowhere else. So we're gonna use the integral test, and let us see how we're gonna use it. So I'm gonna rewrite the series in front of me. So we have it all, k e to the minus k. So ak here is k e to the minus k. So I'm gonna take the function f of x equal x e minus x. Now this function is decreasing. Just use a calculator and sketch it. We will not go over it, spend a lot of time on that issue. So what does the integral test tell me? I have to evaluate the integral from 1 to infinity of x e minus x. If this integral converges, my series will converge. If this integral diverges, my series will diverge. So I have to really compute this integral. So this is equal to what? That's the limit as t goes to infinity of integral from 1 to t x e minus x dx. Right. So now it's really a problem of integration more than anything else. So now I need to find the antiderivative of this function. So let's do that. How can I find the antiderivative of x e minus x? Okay. All right, I need answers. How do you find the antiderivative? Okay, I'm expecting answer. Try by parts. Jordan is absolutely correct. We're gonna do integration by part. All right. So by part, we're gonna put u to be x and dv to be e minus x dx. And the du will become the dx. And v is the antiderivative of e minus x dx, which is minus e minus x. So this is gonna give me uv. It means minus x e minus x minus v du. But I have another minus, which is gonna give me a plus v du. V is e minus x, du is dx. And I have to compute this. So it's gonna give me minus x e minus x. The antiderivative of that is minus e minus x. So now it's just really simple integration. Now I'm gonna go back and evaluate the indefinite integral. So now, sorry, the improper integral. So the integral from 1 to infinity of x e minus x dx become the limit as t goes to infinity of the antiderivative evaluated between 1 and t. So it's the limit of x e minus x minus e minus x evaluated between 1 and t. Questions so far? Sarah? Okay, yeah, fine. Equal. So now let us compute this limit. So that's the limit. As t goes to infinity of the following. T, e to the minus t, minus e to the minus t, minus. At 1, I will have 1, e to the minus 1, minus e to the minus 1. And something is bothering me. You have, that's a plus. You correct me if I did, yes, thank you, thanks. You're right, that's why something was bothering me. Okay, plus that. Okay, what happened when t goes to infinity? It says we analyze it. Let's do it. When t goes to infinity, e to the minus t goes to where? We just did it a minute ago. I'm missing a minus sign. I'm missing a minus sign. So that's minus e plus that. It means this is at the upper limit, minus t plus at the lower limit, if t is equal to 1. I'm missing something, right? That's minus t e minus t plus e minus t minus at the upper limit, at the lower limit, minus e minus 1 plus e minus 1. Something is bothering me. Anybody find a mistake?
I had negative t e to the negative t minus e to the negative t. That's the only difference I see.
I was right. This is a minus here. Yes. Otherwise, the problem isn't making sense to me. Sorry. Now I am fine. Okay, now let us compute. As t goes to infinity, e minus t goes to 0. Agree? Minus t, e minus t, we did it a minute ago. This one also go to 0. So what I'm going to be left with? Minus e to the minus 1, minus e to the minus 1, it means minus 2 e to the minus 1, and the minus here, I'm getting 2 e to the minus 1. So what does this mean? The integral converges since the integral from 1 to infinity of x e minus x dx converge. By the integral test, the series itself converges. Converges. Okay, so we have a series. We are going to know whether it converges or not. The only way we can do it here is by using the integral test. It means compare it to that integral. That integral converges, it means my series converges. Sorry about the stupid mistake. Okay, any other questions before we proceed further? All right. Today we're going to stay a little bit along the same line, and we're going to study something called p-series. There are series that we've seen, not we've seen, but they're going to play an important role in here. What is a p-series? A p-series is a series that have the form sigma 1 over n to the p, where p is a constant. It means 1 plus 2 to the p plus 3 to the p plus 4 to the p plus 5 to the p. Okay, let us see example of that. What does an example? Sigma 1 over n. That's a P series, where P is equal to 1. So that's first example of a P series. Another example of a P series is 1 over square root of n. That's a P series, where P is equal to a half. More example, 1 over n square root of n. Okay, is this a P series? Does it have the form 1 over n to the power something? Yes, because n times square root of n is, let us see that, n times square root of n. It means n root n is n times n to the power a half. Now by adding the power, n to the power 3 halves. So this is sigma 1 over n to the power 3 halves. That's again a P series where the P is equal to 3 halves. Now what about sigma 1 over 2 to the n? Is this a P series? Yes or no? It means, does it have the form 1 over n to a power? Absolutely not. This is actually a what? What type of series this is? This is we're back to a geometric series where the ratio is 1/2. So we have always to know what we're working with. In a P series, it means the power is fixed. The power is a constant, and 1 square root of n to the power a half, and to the power 3 halves. So in a P series, the power is a constant. In a geometric series, the power is actually the variable. That's really what's happening in this case. Now, P series are going to be useful for us. So we will know when they converge and when will they diverge. So here is the statement that we're going to see why it's true. The P series converges when P is strictly bigger than 1. And it diverges when P is less or equal to 1. So this is where to be totally under our control. So the P series converge when P bigger than 1, is diverge when P is less or equal to 1. It's a fact to be used in the rest of this chapter. Now let us see why this is the case. And the only way we can see why this is the case, we have to use the integral test. So what does the integral test tells me? I'm going to take the function 1 over x to the p and compute the improper integral 1 over x to the p. So what's this is equal to? The limit from 1 to t, 1 over xp is x to the minus p dx. And it's a little bit hard because, p is it's a p, so you're going to have some difficulties with that. So it's going to be the limit as t goes to infinity of the antiderivative of that. What's the antiderivative of x to the minus p? 1 over minus p plus 1, x to the minus p plus 1. Just the simple antiderivative. So this is going to give me the limit as t goes to infinity of 1 over minus p plus 1 times, I rewrote minus p plus 1 as 1 over x to the p minus 1 between 1 and t. So fine, it's going to give me the limit of 1 over minus p plus 1, 1 over t to the p minus 1 minus 1. I'll give you a minute to look at it before we start discussing what's really going on. Okay. All right, now I need to find the limit as t goes to infinity. And I'm not going to turn the page. I'm going to ask you questions. What happened when t goes to infinity? I want you to look at it. When t becomes very large, what's going to happen to, this is a constant, no problem with that. My problem is actually here. What happened to this term when t goes to infinity? Okay. All right, I'm having one answer. Somebody is telling me 0. Do you agree with 0? Lori said yes. Anybody else? Everybody said yes. Everybody said yes. Anybody want to say no? It's kind of hard to see. What is hard to see? The writing? Okay, so I'm going to write on a larger piece of paper and analyze it. So you guys have it in front of you. I'm going to write it as it's blurry, okay? Is it any better? Doesn't look like it. Okay, I'm going to write it much bigger. Didn't change. All right, I'm going to write it much bigger so you can see it. So I got the following: 1 over minus p plus 1 over t to the p plus 1 minus 1. Okay, and this is, I want the limit of that as t goes to infinity. All right. Everybody is telling me, Connor, I didn't understand what you said. Power. Okay. What happened as t goes to infinity of this piece? All right, everybody's telling me 0. And now we're getting, it depends on what p is. And let us see why. Suppose I give you p equal to 2. All right, 2. Then this would be 2 minus 1, it's t, it will go to 0. If I give you t to be a half, what will happen? Let us play a little bit of a game. Suppose, I give you p to be equal a half, because p could be anything. And then what will be the problem? I'm going to have 1 over t to the power a half minus 1 minus a half. All right, so this is going to become minus 1. So as t goes to infinity, this is going to go to where? 1 over t to the minus a half is t to the half minus 1. So in this case, at t goes to infinity, this is going to go to infinity. So what's really going to be the problem now? It's going to depend on p minus 1. That's going to play a role. That's really what's going to play a role. If p minus 1 is positive, if this is positive, so now you have 1 over t squared, 1 over t cubed. If this is p minus 1 is positive, this term will go to 0. If p is positive, this will go to 0. Sorry. If p minus 1 is positive, it will go to 0. What if p minus 1 is negative? When I took p equal a half, the p minus 1 became negative. If the power here is negative, when I bring it up, it's going to become positive, and the term will go to infinity. So what I'm trying to say here is that this limit, 1 over t to the p minus 1, it's not 0. It's really going to depend on p. So what's going to be, how is going to depend on p? It's going to depend on p like that. If p minus 1 is positive, it means if p is bigger than 1, then 1 over t to the p minus 1 will be 0, because in this scenario, this piece here is positive. So this will go to 0. And in this case, the integral 1 over t to p minus 1 is going to go to 0. And then in this case, is going to equal to this value, which is a finite value, and the integral converges. However, if p minus 1 is negative, it means if p is strictly less than 1, then p minus 1 is negative. So when you take the limit of that, that's negative. You bring it to the numerator, it will become positive. This limit is infinite. And in this case, the integral will diverge. And if p is equal to 1, integral of 1 over x is just the limit of ln of x. which is plus infinity. So by the integral test, the behavior of the series depends on the integral. But the integral has two cases. When p is bigger than 1, it converges. When p is less or equal to 1, I should add equal here, less or equal to 1, then it automatically diverges. So the p series, which is a series of the form sigma 1 over n to the p, those type of series, they will converge when my p is bigger than 1. And they will diverge if my p is less or equal to 1. Okay, so let's try not to confuse those with the geometric series, which is slightly different. So let us take, for example, questions, very easy questions, just to internalize that. So suppose I give you the following. I'm going to write them here. Sigma 1 over the square root of n, according to the test we just learned. Does the series converge or diverge? First, is it a p series? Yes or no? Yes. Does it converge or diverge? So that's a p series. We're going to rewrite it as 1 over n to the power a half. My p is a half. Does it converge or diverge? P is less than 1, series diverges. Okay, so for those type of series, those very particular type of series, you don't really have to use the integral test anymore unless you want to. If you are unsure, you can just say, you know, it's a p series, and that's really how it is behaving. So let us take another simple example. Suppose I give you 1 over n root n. All right, again, is this a p series? Absolutely, yes. So let us rewrite it as a p series. This is 1 over n to the power 3/2. So, of course, it's a C series, p equal 3/2. Does this one converge or diverge? Immediately, p is bigger than 1. This series converges. It means, what does it mean, convergence to me? It means if I take this series and I start writing up the term, so we never should lose track of what it means to converge. I take 1 and then 1 n equal to 2, 2 root 2, plus 1 over 3 root 3, plus 1 over 4 root 4, plus, if I keep adding those terms, that's what this is telling me. I keep adding those terms. Actually, what happened, I will actually reach a very, very definite answer. It will not blow up on me. However, if I take 1 plus, that's the one I gave you yesterday, I gave you some of its partial sums. 1 over square root of 3, I keep adding those really are gonna blow up. And this is really the difficulty of the subject. I mean, there is no way by looking at it why this one converges, this one diverges. That's why we need those tests. It's hard just to look at it and decide what's really going on in here. Okay, the idea is that those goes to infinity, the general term go to infinity a little bit faster than those, faster enough to make the series converge. But that's not really mathematics. Since p is negative, wouldn't diverge, it's less than 1. Jordan, speak up because I didn't understand. P is not negative. P is 3/2.
It's not negative 3/2 since it's 1 over n?
No, the way we look at it, okay, I understand what your question is. The way the P is what shows up in the denominator. N to the P. That's the P. You don't bring it up and make it negative. So in my problem, it was 1 over n to the power 3/2. That's the P. I don't rewrite it like this and look at the P. Are you with me?
Yes.
That's not the way I'm looking at the P. The P is what shows up down here in the denominator. So P is 3/2 in my scenario. And even if I give you n to the minus 3/2, you should write it as 1 over n to the 3/2 to make it into a P series. So P series is 1 over n to the power P. The P I'm talking about is the P in the denominator, not in the numerator. Understand? Sorry, do you follow?
Yes. I got another question. Will P always be in the denominator?
If it's not, you have to put it to use the P series test. So if I give you, let us say, which I won't, but let us say I have n to the minus 2, right? And I tell you, does this series converge or diverge? You should go ahead and put it as 1 over n squared. Now you know that it converges.
Okay.
Okay, but now if you have something simple, like if I have n squared, just look at this one. Does this one converge or diverge? Just by looking at it. You don't need P series. You don't need anything. What's the general term here? N squared, correct? It means in this scenario, what you'll be adding? 1 plus 2 squared, plus 3 squared, plus 4 squared, plus 5 squared, etc. So what do you think in this scenario? Is it going to converge or diverge?
Diverge.
Absolutely, because the general term, they are really going to become very large. So you're adding 36, like here. You're adding 1 to 4 to 9 to 16 to 25. I mean, you're adding large number. There is no way you can get anything close to a small number. Can I move on, or you still have questions? Please feel comfortable to ask questions. Okay. All right, so that's the P series test. So here I'm telling you, now we know the behavior of two series. The geometric, AR to the N, which is converges when the ratio less than 1, diverges when R bigger or equal to 1, and the P series, 1 over N to the P, converge when P bigger than 1, diverge when P less or equal to 1. So that's really what we know. And we know two things. We know that sometimes we can compare the series to the integral. If the integral converge, the series will converge. And we know the divergence test. So if the terms really don't get close to 0, the series fail to converge. This is all good, but still the tip of the iceberg. Why? What's the problem with the integral test? What do you have to do for the integral test? What do we need to do? Anybody can tell me? We need to do what? We need to integrate, correct? So to use the integral test, we need to find the integral. So if I give you, for example, sigma, one of your problem, which is, I don't know, one of problem is 1 over n ln of n. So in this case, you had to integrate x ln of x. But that was an easy integral. That's a substitution. You put u equal ln and you proceed. Now, let's say if I am very mean, and I give you the following series, okay? I'm gonna give you n squared here, and I'm gonna give you n to the power 3 plus 4 here, okay? So here my function f is x squared over x cubed plus 4. Actually, I can make it more mean, and x6, all right? Eventually, this will decrease. You can graph it. But now, integrating this, what do you think the integral here is? Do we know how to integrate that? And my answer to you is almost impossible. So the question is, if I have this type of series, how can I handle it? So what I'm going to start introducing today is other tests that will help us to determine whether a series converge or diverge. So we're going to see a lot of tests. It's just like integration. When we work with the integral, we saw a lot of techniques. To check whether a series converge or diverge, we're also going to have a lot of techniques. It will not be only one technique. So today we're going to learn a new technique. And the idea behind this technique is, if I give you a series like the one I just gave a minute ago, the idea is we want to try to compare it to a series that I know its behavior, and then go from there. So what is this mathematical idea that helped me to compare what I know, what I have to something I know? Okay, we're going to state there is a theorem called the limit comparison. And it tells me the following. Suppose I have two series with positive term. So the test requires the series to have positive term. And let L be the limit as n tends to infinity of the ratio between an and bn. The theorem tells me that if you compute this limit and you get a number not 0 and not infinity, then the two series, sigma an and sigma bn, they converge together or diverge together. What do I mean by that? It means that if sigma bn converge, then sigma an will also converge. And if sigma bn diverge, then sigma an will also diverge. Now, of course, you did not understand this. I read it and I'll immediately do problem. But this theorem telling me that. Suppose you have a series, sigma n, and you know whether you want to know whether it converge or diverge. You want to compare it to another one that you know its behavior. But what does this comparing mean? You figure out another one that I'm going to tell you how you figure it out. And you compute the ratio between the terms. If this ratio is not 0 and not infinity, then if one converge, the other converge. If one diverge, the other one will diverge. Now, intuitively, why this makes sense, and then how to apply it. Intuitively, why it makes sense. Very, very intuitive basis. So we have this series, two of them, one and the other. And suppose I look at an over bn, the ratio. And suppose L is what happened when n goes to infinity. It means, suppose that when n is large, an over bn is equal to a number, a nice number. This tells that if n is large, an is almost L times bn. That's really what it's intuitively telling me. So if this is the case, it means if an is almost bn, so the theorem tells me then this is almost that. So if this converge, this will converge. If this diverge, this will diverge. That's intuitively what's really going on. So if when n is large, if an over bn is a nice number, it's not 0 or infinity, then my theorem tells you that those two will be the same. If those are an over bn is L, it means an is almost bn. Then if one converge, the other one will converge. So this is a very useful test, and let's see how we are going to use it. So I'm going to take up a problem and explain how we use it. So here's my problem. I'm going to take the series that I played with it, sigma n squared over n to the 6 plus 4. The goal of the series is just to elaborate the idea. My an here is n squared over n to the 6 plus 4. These are this general term of the series. And the idea is that, can I compare this to something I know? What do I mean by that? I said, okay, when n is very large, and that's crucial, an, so this is my an, is actually almost equal to what? Let us analyze it. If n is large, n square is n square. What about n to the 6 plus 4? If n is very large, n to the 6 plus 4 is almost n to the 6. Does this make sense? Yep. Which is equal to 1 over n squared over n6, 1 over n to the power 4. Means when n is very large, those numbers are almost equal to those numbers. That's really what I am telling you. And I'm going to call this Bn. So what I'm going to do now, I'm going to compare this series to that series, sigma Bn. Because intuitively, what I'm telling you that when n is large, those terms are almost those terms. Very, very close in value. So I'm going to compare. I'm going to use the limit comparison test. That's usually abbreviated limit comparison test by comparing sigma an, means this one, to sigma bn. That's the idea. But how can we compare them mathematically correct? What does the limit comparison test tell me? Once you pick your bn that you think behaves like an, you take the limit of the ratio between them. Because I want to make sure that an over bn are very close. And you compute the limit. An is n squared over n to the 6 plus 4. Bn is 1 over n to the 4. So this is going to be equal to the limit as n goes to infinity of. Now we use basic math times n to the 4 over 1, which is going to be equal to the limit as n tends to infinity of n squared times n4 is n to the 6 over n to the 6 plus 4. Now, when n goes to infinity, so this is my L. This is the L of the theorems that you guys should have in front of you. So when n goes to infinity, what is n to the 6 over n to the 6 plus 4 become close to what? If we divide by n6 and n6, this is close to 1. Which means intuitively that when n is large, an over bn is almost 1. It means they are very close in value. So now what does the limit comparison test tell me? So I'm using the limit comparison. So my L in my scenario is 1. The L, to be able to use the limit comparison, your L has to be different from 0 and different from infinity, because they have to be comparable. So L is different from 0 and L is different from pi. So by the limit comparison test, if one converge, the other converge. But now, in my series here, do I know the behavior of sigma Bn? Do I know the behavior of sigma Bn? Sigma Bn is sigma 1 over n to the 4. That's a P series with P equal to 4. It means sigma Bn converge. The limit comparison test tells me in this case, sigma An will have to converge. So the limit comparison test, since sigma Bn, which is sigma 1 over n to the 4, converges because it's a P series with P equal to 4, because this converges by the limit comparison test. Since this series converges, then the original series sigma n squared over n to the 6 plus 4 also converges. So the limit comparison test is about taking the series you want to have and compare it to something you know, basically, something you know. But what does it mean to compare it? It means you take the terms and you ask yourself, when n is large, it behaves like what? So if n is large, this one's going to behave like 1 over n4. Now I check. So this is my first attempt. Then I go and check. Is my choice a good choice? It means it's a good choice if my L is not 0 and not infinity. If you come to 0 or infinity, your choice is a bad choice. So we compute L, the ratio, and I get 1. So this means intuitively for us, AN and BN are very close to each other. Not equal, but they are very close to each other. And the limit comparison will tell me if you are in the situation, then they both behave the same way. If one converges, the other one will. One diverge, the other one will diverge. That's the idea of the limit comparison test. So before I leave you, I'm going to give you like another one, again simple, and I'm going to ask you, we're not going to work it out. If I wanted to use the limit comparison, and I suppose I'm going to put the square root of n here over n squared plus 2. Just for practice, I'm doing those problems just to see how it works. So my an here is the square root of n over n squared plus 2. Now I use the limit comparison test, which is the series I would like to compare it to. I'll give you a minute and then to find it, and then we stop. Okay, I want you to think about it yourself. I want to compare it to something. What should I compare it to? All right, who would like to speak up or write something? I'm having one. Anybody else? Okay, let's do it. Square root of n. Nothing could be done about it. It's 3 square root of n. It's the denominator that we can play with it. So I'm really heading toward a P series, as you realize. When n is large, I can drop. Actually, let me make it a little bit more complicated. Not complicated, actually more interesting. There. I'm going to put 2n. But the problem would not change. Because if n is very, very large, 2n, n squared takes over 2n. So n squared plus 2n will behave like n squared. So even if I had 2n here, it doesn't really matter. It's the term with the highest power that is going to take over. So it's going to give me n squared. So now if I do a little bit of math, that's going to give me 1 over n to the power 3 halves. So my Bn will be 1 over n to the power 3 halves. So that will be the series that I will compare it to. But this is not enough. What I should compare is I should check that my choice is good. And what helped me to check my choice is good is by taking the ratio between those two terms. I have to take the ratio and I have to make sure that an over Bn is not 0 and is not infinity, because if an over bn is very large, I cannot compare an over an to bn. I want a number which is not 0 and not infinity to be able to compare them to each other. So we're gonna compute this limit. I'm out of time. You guys do it. You're gonna get, in this case, you guys will get your 1. It doesn't have to be 1. It could be 2 for that matter. And then this will tell me that because sigma bn converges, sigma an will also converge. So this is a very strong test because it's actually very strong because it actually tells me you can use the knowledge of the P series, you can use your knowledge of geometric series to what? To compare your new series to something you already know. So you don't have to use the other test with you. Okay, that's it for today. Any questions?
Is it true that
for tomorrow? I mean, tomorrow you will have your regular quiz. What I will do is I'm going to put a quiz on Blackboard today. It's like worth 0 point, or let's say it's worth 1 point. And I'm going to call it quiz 0. Okay? And the only thing I'm going to ask you for this quiz, just to practice how to upload on Blackboard, the only thing I'm going to ask you for this quiz is to do the following. Just take a piece of paper, write your name on it, scan it, and send it to me via Blackboard, just to make sure you guys know how to use it. And the way it's going to work is like this. On the content area, I'm going to do it like this afternoon. On the content area, I'm going to introduce a new entry called quizzes. Usually click on it. Once you click on it, then you will have a, I think, because I don't see what you guys see, but what you're going to see something written quiz 0. You click on quiz 0, you will have just a piece of paper from me telling you write your name. Okay, you can either print it if you want, or take a neat sheet of paper, write your name, scan it, or take a picture of it and upload it into Blackboard. I want you to practice how to upload into Blackboard. And send it to me, just out of practice. I'm gonna keep it open. You can make as many attempts as you want, just to get it going. And tomorrow you will have your regular quiz. And any progress on being able to upload the lecture to Blackboard, I haven't had the time to do that. It's gonna be over the weekend. Is that okay? Are you still gonna give us a practice quiz? I don't understand. The practice quiz is just how to do it in Blackboard. Tomorrow you'll have your regular quiz.
Will we be having a lecture tomorrow?
Will you be having what?
A lecture.
Oh yeah, like usual. Everything is like usual. Nothing is gonna change. So the first half an hour tomorrow, I'll answer all your questions because I'm gonna assign homework. I'm gonna answer all your questions, everything like usual. I will stop at 11:30, and 11:30 you guys will start your quiz. I will give you enough time, more time than you need. I'm gonna give you an hour for a quiz that actually will require 20 minutes. I will give you an hour, which is gonna give you plenty of time to take the quiz, upload it into Blackboard. Any other questions?
So today we do the quiz 0 thing.
Yeah, it's just for you to learn how to upload.
Okay.
For those who know how to do it, I don't really care. It's just for those who haven't done it before. I really don't know if you guys have done it or not. So for those who hasn't uploaded a homework on Blackboard before, just to practice with it. Okay, so it's not important. This is just the quiz 0s. I'm gonna ask you write your name, scan it, take a picture and send it. All right, and if you see +1, it means I've received it. And you don't see +1, it means I didn't receive it. Okay, so I try to do it tonight. If you get +1, it means I did receive it. So you know that it's working all right. If I didn't put anything on your grade book, it means I got nothing from it. It means either you know how to do it, or you need to practice more how to do it. Okay, any other questions? Okay, set to go? All right, go have lunch. Bye-bye, guys.